Just a little bit of background about myself. I'm a PhD student, so this is more on the HPC user end rather than on the other sort of provider. But so just to start with, a little brief overview. So beginning with the committer, what this value is, how you can get it, why it's important, what you can do with it, the model system being studied, so the thing we're looking at in order to obtain this committer, the supervising encoder being used, so how we're trying to predict it, the quality of the prediction, and some interpretable insights from those predictions being made, and then finally just a summary. So start with an analogy to chess. So you have a game of chess, play a few turns, freeze the board, and then I'll immediately switch over to some statistical mechanics lingo. So we're going to consider this a microstate, right? It's micro in the sense that it's got microscopic detail, so every single chess piece has an exact location. You want to record it for the entire thing. And then the state. So in the context of chess, you can have four states here where either you have white checkmate, black checkmate, the game is in progress, or a stalemate. And so the committer in this example would be going from sort of either given your microstate, are you going to end up with white winning or black winning? That will be your state B or your state A. And that allows for direct computation of some Wharton values of detail, a bit more on that in a bit. But how could you get this? So a classic way of doing this is brute force computation. So within the context of your chess game, you have your microstate, right? That's your current configuration of the board, and you would launch a bunch of replicas. And so here you have your chess game, you make, I don't know, 1,000 copies, you propagate them all through time, have the games played out, and then you want the committer for that. So you record where each chessboard has ended up, track those outcomes, and the committer is just the ratio of the boards that have ended up with white winning against all of the replicas. Now, a bit of an issue with this is that depending on how complicated your system is, depends how many replicas you need, right? For the chess game, let's say you have, two players, have them play 100,000 games, right? Even then, that's only between two people. There are different strategies, different algorithms you can use. So how do you get that? And a way to do this is if you have the data, you could do some machine learning. So rather than having to brute force it with your replicas and then tracking the outcomes, you just simply go from your X microstate directly to your committer in one single step. So why do this? Why bother at all? So the committer is an optimal reaction coordinate. So it sort of classifies all the information you could want. So here you have sort of X, right? That's where you are currently. Are you going to sync into B? Are you going to sync into A? With Q of X being your committer. But from this committer, you can compute transition rates. And so why is that important? Mechanistic insight, right? So as an example, you have a plane wing. Classic problem here is ice forming on the wing as it's flying. If you have a way of getting the committer, you can get your transition rates. In this context, that would be you have water on the wing. Is it going to turn into ice? Is it not going to turn into ice? And so if you can reliably get that, you can then go, oh, okay, well, if we change, for example, the surface of that plane wing, right, change the material, and then you get the committer, you get your transition rate, you now know the rate at which ice forms. Perhaps, you could reduce the formation of ice. And so what system are we going to do this within? So this would have been an animation, alas, but we're going to be doing this in the 2D ISO model. So you have spins arranged in the lattice. You can think of this as each point being a magnetic moment. Black represents it being aligned down, so spin down. White being spin up, so the magnetic moment is up. You have a field across here, which what sort of is a biasing function, right? That you want the spins or the magnetic moments to align, and you could consider this whole thing to be a magnetic medium. As it evolves through time, you end up with these sorts of clusters growing where the spins sort of pack together, and then you end up with all the spins aligned. And so just on the Hamiltonian, how this works, S is your spin, J is the interaction term between your neighboring spins, H is the field strength, and then that is the energy of your system. Why are we using this one? Well, you want to have rare events occurring. And so often to get good committer estimates, you have to look at these rare events, they're rare events on sort of hour timescales, right? So if I go back to the airplane wing example, you could technically run an MD simulation, right? Molecular dynamics, average of propagate through time, but that would basically take forever. And you'd have to run multiple for different combinations of humidity or temperature and the like. So that's not particularly feasible. And so this system here also has a rare event, but we can in fact compute that, right? And so how do we compute this? We have a bit of a clever GPU implementation for this. Because the Ising model is just 0 or 1, you have either you're in a downspin or an upspin. You can store the information as bits. And then you can design it in such a way that only one core handles an entire grid. And so we can have 18 some thousand on an L40 grids propagating through time all at the same time. So there's a few ways to do this. You can either have it copied over from the CPU each time you want, sort of a bit slow. Next step is to go onto VRAM, but then again, you're slightly bandwidth limited. I mean, these days the bandwidth is not so much of a problem, but then you can avoid that problem entirely by just using the on-chip or on-die shared memory. And so our implementation for this involves, you have your sort of square grid. You could have it just so that every single microstate is represented by its own individual grid. Instead, we implement a sort of multi-spin coding. So you still have one array, but each point on there, rather than being just a single bit, you have a 32-bit integer. And so that is your sort of third dimension, right? So each slice of those bits end up being your own Ising grid. And that's how we can have rather high throughput simulation to get your data. And then guess what is the data that we're looking for? We want to simulate the trajectories. And so as I mentioned with the rare event, you're going from fully spin up state, so the black square, to a fully spin down state to a fully spin up state. That has to go through a rare event process, and this high throughput implementation allows us to get that. As these are being evolved through time, you dump the grids out, you can record or use those for later. Just some context, it's all done in it's a Monte Carlo simulation, the Metropolis algorithm. Those are some parameters to use, but the size of the grid, it's 64 by 64 spins. We have beta of the value there. It's just the inverse statistical temperature, so 1 over T, and then H is your field strength. As that's progressing, we have an output of all of the different microstates. And so once you have your entire data set, this ends up being, you have 18,000 grids, you dump them every sort of, I don't know, in this one's like 100 sweeps, and you run it for 50,000 sweeps, right? End up with quite a lot of data and have to process it. You want to select a portion of your data to actually then calculate the committor for. And so we're going to be using the largest cluster size, a little bit more on that later, but this is a classic sort of collective variable. So the committor is the optimal collective variable. This is a way to estimate it. But once you have your microstates of interest that have been chosen using this classic variable, you then want to run roughly 4,500 grids. Now, why 4,500? Once you've run this many, you end up with an error of about order of % on your final value. And you run sort of all of these. This will allow you to get the committer in just a few seconds. And so hence the model system, right? We can get these quite quickly. Once you have all of the committers, now you have your data set, prune it a bit because you would end up with a lot of your data is not particularly useful, right? A lot of the information will be either in a fully spin down state or a fully spin up state, not particularly useful. So you would prune that slightly, and then that makes your data set for the next step. And so the next step here, going on to our supervised encoder, what are we using? Going to be using a convolutional neural network. And so the immediate inspiration came from image classification. You have a 2D grid. Each one of the points on the grid can be taken as a pixel. Traditionally, in obviously in images, you'd have 3 channels for red, green, and blue. In our context, you just have the one channel, which is the spin. I think another key element is the fact that you can capture long-range interactions, right? That's kind of the key thing here, where you have your fully spin down state, fully spin up state, you have that cluster growing. If you can't look at longer range interactions, you're not going to be able to capture that information. And so this nicely works with it. And then I guess to another reason for why to use these, you want to somehow include physics consistent symmetries, right? This is a physics problem. You ideally would want to use a network that at least has some of these properties built in. And so the convenient thing about convolutional neural networks is that they are translation invariant, or at least can be very easily made to be if you implement them properly. But then you also have rotational invariance and reflection invariance. So in the context of the physics problem, it doesn't matter what you do to that grid, how you move it, how you reflect it, how you rotate it, you should always have the same committer that never changes. And so quite a simple way of having the network learn this is you take your input data and then you rotate it once, twice, 3 times. You perform your symmetries. Well, you form a reflection in the x equals y, and y equals minus x-axis. You've gone from one set of data to 8 times the data. And this sort of allows the network to learn the mapping. Oh, okay, I've switched. It hasn't actually changed anything. And so next up, how does this perform? How are the predictions? So back onto the largest cluster size. This is your classic collective variable for these sorts of problems. As you can see, it works. So mainly, I think here we have a sigmoid fit, right? So all of your, or most of the points sit on this quite nice line. The largest cluster size is a good indicator of how likely am I to end up in this fully spin-up state. And this here is a plot of predicting it. So this is for our training data set. This is for the validation data set. And so you have a bit of an issue where there's some systematic overprediction. This just from here, from the fitting, where you have these points above the line. We could trim them, but then that's just not proper science. But then you have these massively underestimated points. Now, this is a real problem where you have your collective variable, you're using it to estimate your rates, but if your reaction at any point happens to go through one of these, you're just estimating nonsense, right? It's not representative of the actual underlying physics happening. You want to avoid this problem, right? Try and find better collective variables. And so how does the network perform? This here is the same figure that was on the previous slide. This is the convolutional neural network prediction. I guess immediately the root mean square error is nicer, but the key thing here is that there are no real outliers, right? Obviously, there are some, it's not a perfect line, and it ideally shouldn't be in, machine learning applications, but it doesn't have any of these large underpredictions or large overpredictions. How has the network managed to encode its invariance? So the numbers here at the bottom, Ti is the translational invariance. So this is taken across the entire validation set. The number is 0. That's what you'd expect. And then you have rotational, mirror, reflection invariance. This is just an example for one specific grid. As I say, this is across the entire validation set. It just so happens that these two numbers add up nicely to meet the mean committer error. The point here is even if you add those two together, right, even if those errors were additive, you are within this error on the actual committer labels that we have. Doesn't account for the prediction number, but for our purposes, you can consider this to be invariant. How does this compare? So mostly this is another inspiration for the work me and my supervisor have been doing, but from Fang et al. They had basically a very similar application. Instead of trying to predict the committer, they were trying to predict the chance that you nucleate. But in this context, that nucleation where you're, from given your microstate, are you going to end up in a fully spin up state? But they didn't account for, it could go to spin down first before it goes to spin up. The committer does not include that. But we're looking at a comparison of this top line here, looking at L equals 64. This is sort of what they've got, 2,500 parameters, mean square error of 0.05. Our model is a few orders magnitude better, and a few orders magnitude more parameters. I guess the point here isn't to say what we've done is better. The point is that this was done 4 years ago as an offhand thing. Classifier was already showing some promise. We have some better hardware. Why not try this again? See if we can get anything better out of it. I think that the key one for this is that it really matters on the data that you have. And so when doing this project before, didn't have quite the GPU code up to scratch, and the network was just sort of, abysmal at actually getting the prediction. Once you have good data, as classic garbage in, garbage out, thanks to the GPU code, we've been able to actually get a nice data set. And this is starting to get within an area where you can make reliable predictions of the committer, albeit for a simple system, and then from there, get your rates. And on the prediction comparison again, so I just want to highlight these 2 points here, one of them being the best prediction, one of the worst predictions for using the largest cluster size. How does it work? Well, how does it perform? So on the left-hand side, we'll start here with the best prediction. You have the actual value of the committer here. You have the sigmoid, so the estimate from the large cluster size and the convolutional neural network. The largest cluster size is bang on. The convolutional neural network is with an error on the committer. And this here is the saliency map. So basically, what we've got is you make the prediction, sort of backpropagate through, have a look at each input pixel and how much that contributes to the final answer being made. And what's nice to see is that, in fact, the largest cluster is important. But if you look, I'm not sure how well it shows up, the center of the cluster is white. It doesn't have that red highlighting on it. And so that's part of the interpretability of what the largest cluster is a good estimate, but is in fact the middle of the cluster is not important, right? You just want that boundary region. That's what matters when making the prediction. And I mean, this cluster has a bit of a highlight, would make sense. I mean, looking at here, these two clusters, as your simulation is progressing, they're very likely to merge and you would skip, right? So your largest cluster size, imagine that both of those are size 100, your largest cluster size for your system is also 100. But when the time progresses, they merge, you've immediately jumped to 200. It's no longer a good collective variable. And so I guess what we'd like to see here is that we've got a salient schema for this prediction. What is the region of interest? What is important? It's the boundary between those two clusters, right? They're very likely to merge. And hence that's your sort of driving factor for going from a spin down to a spin up state and for actually predicting the committer. What's also of note is this sort of region here and this in the middle, not particularly highlighted by the salient schema map, right? So the convolution on your network does not highlight those as important, which makes sense in this context, right? The real important part is here in between when these two actually merge. And just to summarize, I think I might go a bit fast, but I guess memory management is still important. This is more for any PhD students or people still working on sort of their early careers. We're often not taught, we have the RAM, we have the VRAM. Why do this? Well, we wouldn't be able to generate the amount of data or the training data for our network had we not considered this, right? So it's all on the one die shared memory, and that's due to clever implementation. Neural networks are a promising field for this classification of committers. There has been some more work done on this in recent times, but if we can get reliable estimators for these, we can then get reliable physical insight predictions, and then, well, just for acknowledgements, I'd like to thank my supervisor, David Quigley, EPSRC for their funding, and then the University of Warwick SCRTP and HPC Midlands SULIS for their compute. Thank you for listening.
Thank you, Hubert. Any questions?
This one.
Yes.
Yeah.
So I guess I'm a bit not into the field, but to get the committer, you cannot use any more efficient algorithm like Wolf or that will swap many things at the time. That's the reason you have to go so more brute force, right?
So it depends on what you're trying to get the committer in, right? So Wolf would work quite nicely for the Ising model, but even then it's still quite a slow process. So you could speed up individual calculation, but it's more of a testbed system to see how this works, right? Bit of a learning opportunity. But yes, it would make this faster, but only for this specific style of application. So
Thanks.
Any other questions? Okay, thank you, Hubert.